calculate percent abundance. And Mr. Isotope Enthusiast, we're talking about characteristics of an atom. And one of the ways we can categorize different atoms are by their masses. Let's look at this particular isotope of carbon. This carbon isotope has a mass number of 12. Okay? And we know that carbon always has 6 protons. So if the mass number is 12, what does that mean about our number of neutrons?
Also be 6.
Also be 6. And this is a different isotope of carbon. It has a mass number of 13, but does our proton number change in this? No. Our protons are permanent, so the only thing that changes are the neutrons. And here we have, instead of 6 neutrons, we have 7. So this carbon weighs heavier than this carbon does, right?
Yes.
So if we were talking about the mass number for carbon, what would that be? 12. And if we were talking about the mass number for carbon, what would that be? 13. Okay, so I'm going to bring in kind of an interesting element. Here is the symbol for carbon that we see on the periodic table. We've talked about this number. What is this number?
Then it's the atomic number.
Right, and it's, if I asked you to calculate the average atomic mass of all of the carbon isotopes, you might do something like this. You might say, well, this carbon weighs 12, this carbon weighs 13, there's 2 of them, let's add together, divide by 2, and we get 12.5 AMUs, right? And you might say, hey, that's the average atomic mass. Well, unfortunately, it doesn't quite work that way because we're not taking into consideration the number of carbon atoms that are at 12 and the number of carbon atoms that are at 13. This is assuming that there's equal numbers of carbon 12 and equal numbers of carbon 13, right? Okay, so let's take a look at this scenario. Let's say that we have 9 carbon atoms that weigh a mass of 12 AMUs, and we have 1 carbon atom that weighs a mass of 13 AMUs. If we were going to try to calculate the average mass, okay, so one way you would do this to solve it is you would set it up like this. Because I have 9 carbon 12s, it wouldn't be fair just to do 12 plus 13 divided by 2. Because I have more 12s than I have 13s. So I want to take that into consideration. So since I have 9 carbons that are at 12 AMUs each, I just write out 12 9 times. And I only have 1 carbon that's at 13, so I would write it like this. So here's one way I could do it. I have 10 carbon atoms. This is the weight of each isotope right here on the top. And here are the total number of isotopes. Okay, here's your total number of isotopes. So when I do the math, I end up with 12.1 AMUs is the average mass. And when we look at the picture on the periodic table, we see that we're really close. 12.011 is very close to 12.1. So whenever you're calculating average atomic mass, you have to take into consideration how many of each carbon and how many of each other carbon you have. Okay. So this seems kind of like a long and annoying way to work out this problem. Let me show you a way that we can do it faster. Instead of writing out that long equation, you can just shorten it by writing it like this. Here is the number of isotopes that weigh 12 AMUs. We have 9 of them, right? So instead of just adding together 12 9 times, I might as well just multiply it. So I do 9, which is the number of isotopes, and then 12 is the weight of those 9.
Yes.
Okay. And then here, I only have 1 that weighs 13 AMUs. So this is the number of isotopes that weigh 13 AMUs, and then that's my weight. And again, here I have my total number of isotopes. So when I do the calculation, again, I'll end up with 12.1 AMUs as my atomic. Okay, let's say instead of numbers of carbon atoms, I had percentages, because there's really no way for us to count how many carbon atoms are at a mass of 12 and how many carbon atoms are at a mass of 13. But we do know percentages. So what would happen if I said 99.9% of carbon have a mass of 12 and 0.1% of carbon has a mass of 13, and I asked you to calculate the average mass? This is going to be the number of carbons that are at 12. So I'm going to write it out like this. Instead of having the number like this, because it's a percentage, I write it down as a decimal. So here's my percentage written as a decimal. Okay, so here is the number, the percentage of carbon 12 but I wrote it as a decimal. And this right here is the mass of that isotope at that percentage. Does that make sense? And then I'm going to add that to, here's my percentage as a decimal for carbon-13, and here's the mass of the carbon-13 isotope. And I don't have to do the divide and by, because instead of a number, I'm dealing with percentages. So to find the average atomic mass of these two carbons, I transfer the percentages to be decimals, and then I take the masses of these two carbons and multiply them by that percentage. When I get those numbers, I'll add them together, and I will still end up with 12.011 as the atomic mass of the carbon. Let's do a couple sample problems. Gallium has two main isotopes. The first one is gallium-69, and the second one is gallium-71. Okay? And there's 60.11% of all gallium atoms are gallium-69. Okay? And 39.89% of all gallium atoms weigh 71. They're gallium-71. Okay? So this is, in effect, our percent abundance. So whenever I talk about the percent abundance of an isotope, I'm really just talking about the percentage of atoms that are that isotope. Okay? So, here's my percent abundance for my two isotopes. It's asking me to find what's the average mass. Well, before you get started, I want us to notice that 60% of all the atoms are at weigh 69, and only like 40% weigh 71. So what do you think the average is going to be closer to? Do you think it'll be closer to gallium-69? Yes. Or closer to gallium-71?
69.
Why?
Because of a bigger number, this majority of it.
More of the atoms are that weight.
Yes.
So the average should kind of tend to move that way, lean that way, yeah. Okay, so if I asked you to calculate the average atomic mass of gallium, what would be your very first step?
Multiply the amount of gallium-69 you have times 69.
Right, so instead of, remember, when I'm setting it up, I'm not going to put this in as a percentage, I'm going to put the percentage in as a decimal. And I don't know if we mentioned this, but when you're trying to make the percentage into a decimal, you just move the decimal over twice, and then 60.11% is the same as 0.6011, right? Because this is essentially over 100. So that's what it should look like. So here's my amount. That's my percentage as a decimal. Okay. And what is this number?
It's the isotope mass.
Of gallium-69,
yes.
Right? Okay. So I'm going to take this, and I'm going to add it to the percentage of gallium-71 as a decimal times the actual mass of gallium-71. When you plug this into the calculator, you should get 69.7 AMUs is the average mass. Now 69.7, is that closer to 69 or closer to 71?
Closer to 69.
Which is kind of what we predicted, right? And when you look on the periodic table, you see gallium, the average mass is 69.72. So exactly what we calculated.